Okay, so this first video is going to briefly talk about some concepts that are sort of introductory to equilibrium, sort of build upon the simulations we did in class. So without further ado, let's get started. Now, so hopefully you do realize that an equilibrium is a series of two different reactions. So we can look at the first reaction as we start with some certain amount of reactant, and it's going to proceed. As the reaction proceeds, the rate of that reaction decreases, and we get a curve something like that. Maybe not a little quite so flat line, but again, we know this from rates. You can calculate the different rates of reaction, and that rate should decrease over time, and you get to this plateau where the rate is basically constant, so there's no change in rate. And we now hopefully realize that those reactants produce products. Well, those products can start reacting as well, and that might look something like this, and they're producing reactants, and once again that rate is changing over time as the reaction proceeds. Those former reactants that became products, and now products reacting to produce reactants. And so what you get at some stage is a point where the rates of both reactions are equal. And so that is are not equilibrium, are equal. And so the situation we are interested in now is this equilibrium, and how we actually do have still two different reactions taking place, but the rates at which they take place are equal. So this is essentially what we're looking at. You might have a graph that looks a bit like that from one of the simulations. So to illustrate this, we use this double arrow. So when you see that double arrow now, you must realize it's an equilibrium situation. So the double arrow tells us we have a reversible reaction. And so we have two reactions, a forward reaction and a back reaction. So in our simple context here, air plus B yielding C plus D, well, that's just the way it was written. I could have just as easily written as C plus D yields A plus B. And so in one direction I have a forward reaction, in the other direction I have a back reaction. But for all intents and purposes, it doesn't matter which way you write this. You could still write it C plus D. It just becomes a forward reaction. But what we have is two reactions. What's important here is formation of products and the reformation of reactants. That's the back reaction, or opposing reactions. And that's what an equilibrium is, opposing reaction. And this occurs in what's known as a closed system. And you should appreciate what a closed system is, and I'll talk about that in a minute. So conditions do apply for equilibrium. Equilibrium is achieved by a reversible process. So it has to be reversible. Not everything is reversible. And so we're really looking at certain types of reactions. There are certain reactions. And equilibrium is achieved when the rates of the opposing changes are equal. Okay, and that's the double arrow. So the double arrow indicates at equilibrium. For a system of equilibrium, the observable or macroscopic properties are constant, and you do not see a change there. So the macroscopic properties we might look for are things like color change, a pressure change, or a concentration. And if we can observe or measure those, we would see that there would be changes taking place until the system reaches equilibrium. But at equilibrium, there are no changes. So those two conditions I've just mentioned are summarized as saying you have a dynamic equilibrium that involves changes at the molecular level, right? Changes at molecular level are two reactions opposing one another, but no changes at the macroscopic level. And so one of the common misconceptions in equilibrium is that the reaction is stopped. Well, the reaction is not stopped because it's dynamic, And another misconception is that you have equal concentrations, and nowhere does it indicate that the concentrations have to be equal. Concentrations are quite likely not to be equal at an equilibrium. So achieving a constant or equal concentration is not a component of equilibrium, but achieving no changes in concentration, as I've indicated here, is a factor of equilibrium. Now, two other things. Equilibrium can only be reached in a closed system, so I mentioned that before. And what's a closed system? The system does not allow for the input or removal of any component of the equilibrium system, so that would include energy. And so by any component, what do we mean here? Well, a component of a system would be, say, adding more of a reactant, because we've changed the system, the nature of the system, by adding some extra reactant, or removing something. That would be a change in the equilibrium. We're going to look at what happens when we do change an equilibrium system, but equilibrium has to be achieved in a closed system. And equilibrium can be achieved from either direction. And so I can just show this here. So in this scenario, we have an Erlenmeyer flask, and we can add some water to that flask, just liquid water. So put a bit of liquid in there, and then we seal it. So now I have a closed system. And so over some period of time, I'm going to have that water, but I'm also going to have some water vapor. So the water evaporates, and I get some water vapor. Well, as soon as that water vapor is present, it can start condensing and go back into the liquid phase. And so at some stage, I'm going to reach an equilibrium between H2O liquid and H2O gas. And so I start with the liquid state only, I seal it, and still in the closed system it starts vaporizing, and then I have the equilibrium there. Well, I can also start with a beaker that I put in only water vapor, and I seal it. And once I've sealed it, I have a bunch of water vapor in here, and it's going to start condensing, and so eventually I will get the same situation. I'll get the same equilibrium. I'll get a combination of water vapor and liquid water. So again, it doesn't matter which direction you approach an equilibrium, it will reach equilibrium from either side, either way. And so that's all I'm going to say on this brief little video, this introductory video. So I guess that concludes this video.